he will be talking about he will be talking about the failure of Gorensteinness at weight 1 Eisenstein points of the eigencurve. So thank you, Adel, and you can start.
Thank you a lot for the invitation. And I will start now by introducing the background. Sorry, just a question. I have 40 minutes for the background, if I understood well, and 40 minutes for the talk.
Yes, exactly.
Perfect. Thank you a lot. So for the background, I will use my tablet. And for the talk, I will use the beamer. So I will switch when I will finish the background.
Okay.
So, perfect, it works. You can read, it's fine.
Yeah, it's fine. Yeah, it's perfect. Fine.
So I will start my talk by recalling the basic stuff in arithmetic geometry, like modular forms, elliptic curves, and the connection between them. I will start now by elliptic curves. And they need some notations. For me, P and L will be always prime numbers. And of course, P will be always different from L. And K will be filled. So we'll start with the first definition. Sorry, I don't know what's happening. 1 second. So yeah, sorry, I had a small problem. Oh, sorry, I don't know what happened. I have to switch to another one. I apologize. So I will start with the first definition. An elliptic curve E over K is smooth, projective curve of genus 1 with a base point. I will give examples and then you can think just about the examples if you don't know the terminology. So, I mean, the precise definition is a scheme of dimension 1 over K, which is smooth and projective and of genus 1, and it has a base point, I mean, a K point. The genus is just the dimension this is the genus, is the dimension of the global sections of the differential sheaf on E. This is the genius. And I will give many examples. So the first example, take K equal Q, and take this equation, y square and x minus lambda equals 0. This is what we call the affine part of an elliptic curve. I mean, you take you see this inside the affine line of dimension 2, but you can then take the closure in the projective space, and the closure will be really an elliptic curve, but you add just one point to the affine part. So you can think of it as the zeros of such equation. It's you can see it inside the affine space, which is inside the projective space. And I mean, if you take it like this, it is an affine, it is not projective. But if you take the closure in the projective space, you add just one point at the infinity, you will get what we call an elliptic curve. And in general, it has, I mean, this is the first example. In general, you can write directly the Weierstrass equation of an elliptic curve in the projective space. Now, which is a little bit long. With A1 until A6 in K is any field. But you take here really the equation, you see it as an equation in the projective space. So the zeros inside the projective space. I mean, when I put here V, I mean, I take the zeros inside the projective space. P2, which is proj of K X, Y, Z. And you can see it's an homogeneous equation. And if you have a zero, any multiple of your zero by, sorry, if you have a point X, Y, Z, which is a zero, any multiple of your point by lambda, which is a scalar in K, will remain a zero because the equation here is homogeneous. And it is a cubic inside the two-dimensional projective space. And it's called the Weierstrass equation of an elliptic curve. I mean, in general, an elliptic curve can be written as this, but you have another condition on the coefficients. I didn't write it, but you can associate to A1, A6 a discriminant, and you impose that the discriminant is non-zero. Otherwise, you can have a singular cubic. And here you have this, and you have the discriminant is non-zero. I will not give the formula because it's quite long, but you need this condition to get the smoothness. And the third well-known example comes from is a Riemann surface of genus 1. So I will introduce a notation that I will use after. I will take HB, the complex numbers, such that the imaginary part of Z here is positive. It's the Poincaré half plane. Pick here tau, an element in H, and set L tau be the following lattice inside C. Then the quotient of C by this lattice is a Riemann surface of genus 1, and it is an elliptic curve. It is the complex point of an elliptic curve. And you can, if you take an elliptic curve over Q and then you base change it to C, so you look to the zeros over C, not only over Q or an algebraic extension of Q, you get a Riemann surface having the following uniformization. We call this the complex uniformization. And you can see from here that you have you can see here that this is an abelian group. And even you can show in general, if you take an elliptic curve over Q, over K, then the points of your elliptic curve is an abelian group. And is there some questions? And so I want to ask you, is it readable also, or should I write bigger? Or
I think it's readable. I think it's clear.
Perfect, thank you. Now I want to develop a little bit more the theory of elliptic curves over Q. So let now E be an elliptic curve over Q. Elliptic curve, and set Tp of E is called the Tate module as the limit of the P-n torsion unit, limit over n, and this is isomorphic to Zp square, where Zp Zp is the completion of Z with respect to the maximal ideal P. You can think you take Z, you take the localization at P, you get a local ring, and then you take the completion with respect to P. I mean, in the p-adic topology, P power n goes to 0. In the p-adic topology, for us, the limit is 0. And here you can see already example, if you take a Riemann surface, you can see from, you can calculate what is the P-n torsion. It will be, if you take n, the P-n torsion, it will be 1 over P-n, the lattice that I used. And if you take the limit, you will get necessarily Z mod P-n square, and you take the limit on n, so you get Zp square. And here, the lattice, you can think of it as the H1 of the homology of your Riemann surface. And here we have similarly, if we work over Q, we have the Tate module will be the dual of the étale cohomology. You take here what we call the étale cohomology. It will be the dual of it. In schemes theory, the étale cohomology somehow substitute to the Betti cohomology or the singular cohomology. But it has a nice structure, which is the action of the Galois group, because here the Galois group of Q bar over Q acts on the TP. Because the Galois group will act on Q bar. And here what I mean by EQ bar, the solutions of your elliptic curve in Q bar. And since the coefficients are in Q, when you act on the solution by an element by an automorphism who will fix Q, it will not move the coefficients. So the image of any solution under conjugation by an element of the Galois group will remain a solution. And you can think of it as this. And then you get an action, acts, and even this gives to a Galois representation of GQ, which is the Galois group of Q bar over Q into GL2 ZP, because the Tate module is ZP square, and the Galois group acts on it, so you get directly a Galois representation. And this Galois representation is continuous somehow if you put a topology in the Galois group, which is the Cruel topology, and the p-adic topology here in ZP square. Under the two, this representation is continuous. And this representation has many interesting properties. I cannot list them, but they are they come from the world of p-adic Hodge theory, which are somehow analog to the complex Hodge theory. And I want to highlight also something which is quite important. For almost all primes L away from P, the trace of this representation will be n-ramified at L, and then you can consider the evaluation at the Frobenius. Is exactly I will explain here a little bit. I mean, if you take this Galois representation, you have, you have canonical, you have natural elements in the Galois group called the Frobenius, but somehow they are not, they are defined up to conjugation. But if you take the trace, it's fine. But you need to know also that your representation is n-ramified, which is the case here. Then you can look to the trace evaluated at such Frobenius, and you have explicit formula. It will be L plus 1 minus the number of solutions in FL, the residue field of characteristic L, of your elliptic curve mod L, because then you can reduce your coefficients, which are integers. You reduce the mod L, you get an elliptic curve over FL, and here it's the number of solutions in FL and not the finite extension, exactly in FL. And this is somehow an analog of Brouwer theorem about fixed points, but in the étale cohomology. This follows from Lefschetz theorem. I mean. So you can see that this Galois representations has many properties out at has nice properties at almost all the primes. It's n-ramified, and the trace is related to the reduction of the elliptic curve mod L. But at P, the properties are more complicated. It's what we call the RAM or semi-stable or stuff like this. I will not explain them. Now I will discuss what is a modular form and the relation with elliptic curves. So now I will start the second part of the background. Modular forms. Here it's important. I will add gel to Q. Because in general, for any reductive algebraic group, you have a theory of automorphic forms and then modular forms. But for today, we'll discuss just what we call elliptic modular forms, which are over GL2Q. And I need to introduce some notations. So I need to change the color. So let SL2Z be the following group. All the gamma A, B, C, D with coefficient in Z such that the determinant of gamma is 1. And I will introduce some specific subgroups of SL2Z called often in the literature as congruent subgroups. So for n greater or equal to 2, set gamma 0 n with all the gamma here, A, B, C, D, already in SL2, and C is congruent to 0 mod n. So I mean, if you reduce this, the coefficients modulo n, you will have upper triangular matrices. And gamma 1, which is a sub also of gamma 0. Now A, B, C, D in gamma 0 n, and D here is congruent to A to 1 mod n. So matrices which are unipotent modulo n, and they are all and they have all a finite index in SL2Z. So now I have to start a new page. So I recall that H is the Poincaré half plane. Sorry, the imaginary part of Z is positive. And I will sketch a picture here. So here you have, if you write Z as X plus EY, you have here the X axis and you have the Y axis. And the Poincaré half plane will be just this one. I mean, the imaginary, I mean, Y is positive. And the idea is like this SL2Z acts naturally on H as follows. So if you take gamma applied to Z, if you take gamma here, A, B, C, D, and Z in H, then you act as follow. Gamma Z will be AZ plus B quotient over CZ plus D. I mean, this will remain also in H. And the quotient will be a complex, you can endow the quotient with a complex manifold structure. The quotient will be of dimension 1 and over C, and it will be a complex manifold, but it will not be compact. So we want somehow to add points to make it compact. To follow somehow the compactification following the method of Alexandrov. So the idea is to add few more opens and some points to make it such that the quotient will be compact. So what we want to consider, the following. We take H bar and we add, it is H, this joint union with P1Q. I mean, how you can see P1Q here, you see it as follow. As Q union infinity. And somehow the Q is, I mean, if you take here, say, alpha over beta here, you add points like rational points here, there in Q, and infinity is here. I mean, we need to add somehow a neighborhood of infinity. For us, the infinity will be, we'll see it as when y goes to infinity, only y. So for us, a neighborhood of infinity will be the following. If you take when y is quite big, we consider it as a neighborhood of infinity, but we add infinity because we consider this as a set. We have already the topology here on H, and we add a few opens. We add this P1Q, which is a discrete set, and Q we see it naturally as in the x-axis, and we have this infinity, and we add more opens to in H bar. We have already topology of H, and we add more opens. For infinity, we add the neighborhood of infinity as follow. We take we'll denote it by DH, say. Sorry, H union, sorry, infinity. No, sorry, I didn't define it. Sorry, I wrote something stupid here. So it's this one union infinity. So you take like all the elements Z such that the imaginary part of Z, I mean Y, is bigger than H, and you add infinity. And this is somehow, and this is an open of, it will be an open of H bar. So now we will add many opens and take the topology generated by such opens. And for the elements here, we add the disk, which is tangent, a disk which is tangent to the element here. And why we do this? Because we can always get a gamma in SL2Z who will send us, will send the neighborhood of infinity to a disk like this. So the idea, this topology is somehow preserved by the action of SL2Z, because I can extend the action of SL2Z on H bar. And then the quotient can be endowed with, it will be a compact Riemann surface. And in this setting, it will be just the projective space. But if you take gamma 1n or gamma 0n, you will get Riemann surfaces with a certain genus that we can compute using Hurwitz formula. But the idea is as follows. We need really to add P1Q. We call them cusps. And then we extend the topology. So we define what is the neighborhood of infinity and the neighborhood of rational numbers here in the x-axis. And we consider the quotient by SL2Z, and we get we can undo this quotient with a structure of a complex manifold. And I want also to highlight something here. If you consider the map, it's a small remark here. If you consider this map, So if you consider this map from dh minus infinity, so we take just a complex number such that their imaginary part is strictly bigger than h, you can send them to the disk of center 0, the open disk, minus 0. You have a map, we'll send an element z here, and you take exponential and somehow you can extend this map to infinity, and infinity you will send it to 0. You can see here you have, I mean, here you have the disk, but you remove the origin. But when y goes to infinity, the limit will be really the origin. Now I will define what is a modular form. So I need to fix k, which is the weight of the modular form. I mean, it's just a notation here. For me, it's like level gamma 1 or gamma 0. If first f is holomorphic, so analytic, and the second condition is I have this f satisfies this cocycle condition, cz plus d fz for all gamma a, b, c, d in I mean, if I put here gamma 1 and I should have it for any gamma in gamma 1, and if it is gamma 0, I should have it for any element in gamma 0. And the third condition, f is f is holomorphic at the cusps. I mean, here the word holomorphic here looks a little bit weird, but I mean, the limit at the cusps, either which are cusps which are rational here or infinity, exist. But then, so this exponential map that I defined here, you can see then f as a function on these disks minus the origin, and you get somehow like I mean, you get really something holomorphic. You can extend it even to the origin. Because in general, you get just a Laurent series, but then you can extend it to the origin. I will explain this in details. And I want just to highlight again that if you have a neighborhood of infinity here, you can find an element in SL2Z. And when you apply this neighborhood you apply this element in SL2Z to this neighborhood, you get a neighborhood of a cusp, a rational cusp here. So you can send this DH to a disk which is tangent to a cusp in here in the x-axis. And here, when I say holomorphic, I mean, you at infinity, it's quite direct. You check just the limit when y goes to infinity. Then when you want to check the limit at the cusps in the x-axis here, you need to apply this gamma from SL to Z, such that you send a neighborhood of your cusp in the x-axis to a neighborhood of infinity. You apply this gamma, and then you check, you have this f gamma z, and you check now the limit of f gamma z, whether this limit exists when the imaginary part of z goes to infinity. I will introduce now the Q expansion, which is quite important. Now, since we have 1, 1, 0, 1 in gamma, we get this property fz plus 1 equal f of z. And then you can write, using Fourier analysis, you can write fz as big FQ and as follows: sum Qn and in Z. And Q here is, I mean, Q, you can write it exponential. And so, as I explained before, Q, you can see it as the variable of this disk. This will correspond to my Q. And here I want to make this map bijection. I want just to consider just the part where x is between 0 and 1. Here it's 1. Because this exponential is periodic with respect to x. And then if I consider just this strip, with the exponential, it will send it to this disk minus 0. But if you extend, if you add infinity, the infinity will go to exactly 0. And then you can check that this f is holomorphic, and then it has a, at the beginning you check that it is holomorphic outside 0. So it has, you can write it as follow. It has a Laurent development. But since we said f, we impose that this condition holomorphic, then you can here do better. N is greater or equal to 0. You don't have a pole. I mean, you don't have 1 over q or 1 over q square. And q here is exponential to z pz. And the IN are called the Fourier coefficient. So sorry, I need to add f here because the Fourier coefficient of f. And the Fourier coefficient determines uniquely f. So now I need to introduce the notion of an eigenform, which is an eigenform is a specific modular form. Sorry, in the definition of modular form, I forgot to add the weight and weight k. Sorry, weight k. So I mean the weight shows up here. So you fix k, and you have the weight and the level for which you have this automorphic. Sorry, this cocycle. I mean, f looks like a cocycle. So now I introduce the notion of an eigenform. I need to introduce what we call Hecke operators. So you have the first Hecke operator, which is called the diamond. I just remind you that I mean, here we have an isomorphism. We'll send like A, B, C, D to D mod N. And then if you take the space of modular forms of level gamma 1n, you can act then on it by gamma 0, but this action will factor through gamma 1n because of this cocycle condition. I mean here, because I mean, you impose that you act by, you put gamma here and you take this, the factor in the other side. Then the action, I mean, fixes gamma 1n, but gamma 0 will act maybe non-trivially. And then this action will factor through this finite group, and then you can decompose it in terms of eigenspaces. So you can write this one as the sum on all the characters of Z mod n Z star. And here you get modular forms of level gamma 0 n and character phi. I mean, here, if you look to the action, it's the same like the condition 2, but you add, if you take an element here, if you take f here, you have something similar to the condition 2, but you need to add here the character. You will have like phi of d. And so if you and you can really decompose your spaces for gamma 1n as this sum. And this action is called the diamond action. Often it is denoted like this when you take a d like this. And f here, if I take f here, it means f is an eigenvector for the diamond with respect to the character phi. Now we have also, I mean, we have this is the first important action that we need, and we have a second one, which is the Hecke operators. Now, for any n in Z that is equal to 1, there exists a correspondence. So I haven't the time to explain all the details, but there is an operator. I will give just the main properties of this operator. I can define directly the action on the Q expansion. If I take Fz as the sum of an f qn, I told you Q here is exponential z. Tn of f will be again a modular form. And if you look to the Q expansion of it, you can recover it from the first one as follows. Sorry, Tm. Here I put m. Tmf. And you can check easily that the Tn and Tm commutes. So you can consider the subring of the endomorphism of the space of modular forms generated by the Hecke operators, and you get a commutative algebra. And T1 here is the identity. So, I mean, this is the formula, but in general, the Hecke operators are really correspondences on the quotient of this Poincare half plane by gamma 1n, and from the correspondences, you can check that on they act on modular forms as follow on the Q expansion. But you can define it also like this. But if you define it like this, it will be a little bit hard to check that what you obtain is a modular form. And now, for me, an eigenform is a modular form, which is an eigenvector for all the Hecke operators outside the level of the modular form, which is n. So Here, the n, it's the one occurring in the level. And f is an eigenform if and only if it is an eigenvector for all the Hecke operators outside from n. And I want to highlight here, I have not time to explain it, but such Hecke operators are semi-simple because they admit an adjoint under a certain pairing. And you have always a basis of eigenforms. This space admits a basis of eigenforms. Can get always a basis. It is of finite dimension over C and has a basis of eigenforms. Eigenforms, I mean, it's an eigenvector for all the Hecke operators, and which is quite nice. Now, if A1 of f is 1, you can normalize it such that will be always the case. Then alpha n is an of f. An of f is the Fourier coefficient. If in addition the first term is A1 of f is 1, then the eigenvalue here is the one is the Fourier coefficient for the integer n, for the integer n. And now, I mean, I will give you I will state here an important theorem. That the first Fourier coefficient is 1. Then there exists a Galois representation QP is the fraction field of ZP, and QP bar is the algebraic closure. But in general, it lives in a finite extension of QP. But I mean, such that we have this important property. I mean, if f is an eigenform with A1 f equal 1, I mean, it's a normal, we call it often normalized eigenform, then there exists a Galois representation from the Galois group of Q to GL2 QP bar, such that the trace of your Galois, such that the Galois representation is unramified at all the primes L away from N and P, and the trace of your Galois representation evaluated at the Frobenius at L is the Fourier coefficient. So more or less, this Galois representation will recover almost all the Fourier coefficients of f. And if f is new, I mean, it doesn't come from, it's not a modular form for m, and m is m divides n, then it will recover all the coefficients. And now I will explain you just I will just introduce a picture about the Langlands program. I mean, the Langlands program is the following. Sorry, before I need just to add one word. Sorry, here I forgot. Here I need to add just one definition. What does mean a cuspidal modular form? It's important. F in MK is cuspidal if F vanishes at the cusps. I mean, if you write the Fourier expansion at any cusp, infinity and other cusps, the constant term is 0. And if F is cuspidal, we have an important property. The Galois representation here is irreducible. And now I can just give you a picture of weight k. In the long program, there is a correspondence between such cuspidal eigenforms of weight k and Galois representations with certain properties in Pedical theory of Hodge state weight 0, k minus 1, and theorem at p. Somehow, I mean, one of them is already done in this theorem. I mean, it is a theorem of Eschler-Shimura and Deligne. Example, if the weight is 2, they attach to the modular form an abelian variety, and they take the Tate module. You get such a representation. And inside this program, you have the conjecture of Taniyama-Shimura. If you add here, you take the weight is 2 plus coefficients in Q, coefficients of your modular form, I mean, in the Fourier expression in Q, you should get here elliptic curves. Those correspond to elliptic curves, and the elliptic curves, they have a Galois representation, as I explained. If you take E here, you have rho E here. And one direction I told you was done since a while, and the other direction, here it's called the Fontaine-Mazur conjecture in general. And here, for elliptic curves, it's called Shimura-Taniyama conjecture, and it was done by Weiss. So now I will I will switch to my beamer, and I will.
Excuse me, Adel.
Yes.
It just we can pass to a part of question about this first part.
Of course, yeah, of course, yeah. So sorry, so I need to open my tablet again. Sorry.
Yeah,
I went quick. Sorry. Yes, sorry.
Take your time. Yeah.
So one
second.
So now I will speak about a project that I conducted with two collaborators, Nad and Dimitrov in Lille and Adel Pozzi in London. It is about the geometry of a modular space called the eigencurve. It parametrizes deformations of modular forms. Now I need to introduce also some notations. I'm sorry, I cannot also introduce everything, but I will try at least to give characterizations of the object. So I start by a character called the p-adic cyclotomic character. Here, I mean, I adjoin to Q all the Pn roots of the unity. I get somehow a Galois group isomorphic itself to Zp star. And Zp star is the units in Zp. And the Th, and here I have the Th-Müller character. Here I adjust the P roots of the unity. The main property of the cyclotomic character is the following. It is unramified outside P, and the evaluation at the Frobenius is L. Sorry, the Frobenius at L is L. And I mean, because Zp is a Hanselian local ring, so I have this decompositions. If I take the units, I have here the units of the residue field. I mean, I can lift them uniquely to Zp star, which is a discrete part, and this one is a torsion-free part, which is abstractly isomorphic to Zp. This is itself is a proper group of, isomorphic to Zp. If you take, example, the logarithm, the p-adic logarithm, you will get pZp, and you divide it by p, you normalize it by p, you get Zp. And 1 plus p is a topological generator here. And the Th-Müller is just the post-composed of the cyclotomic character here with respect to the projection to the discrete part. And lambda here will be the one variable Iwasawa algebra. You can see the formal power series with coefficient in Zp bar. Zp bar is the closure of Zp. Or you can think here you take finite extension of Zp, which remains a discrete valuation ring. And it is also the group ring attached to this Galois group. And we have specialization, a specialization map sending for any k, sending x to this to 1 plus p power k minus 1 minus 1. And the idea is like we want to, I mean, I forgot to say it before, but if you take an eigenform, the Fourier coefficients are rational. And often they are even integral. And the idea, we want to deform them p-adically. I mean, with respect to the p-adic topology. Then for me, like two numbers are close p-adically if the difference is divisible by high power of p. So for me, example, the weight example k and k plus p are somehow neighbor because the difference is already divisible by p. And if the example take k and k plus p power 1 million, they are really close for the p-adic topology. And the first tentative to deform p-adically modular forms was done by Hida, Harisu Hida, and it's called even Hida theory of lambda-adic families. So I will explain you this lambda-adic family. The lambda-adic family f of level n and n by t plus phi can be seen as an abstract Q expansion with coefficient in lambda, such that the specializations that I defined before for any k greater or equal to 2 is the Fourier expansion of a modular form of weight k. So you can imagine you have somehow Q expansion, but with coefficient in this Iwasawa algebra. And if you take the specialization for k greater or equal to 2, you get the Q expansion of a modular form here. And we denote by m and phi lambda for the lambda module of lambda-adic families of level n and n by t plus phi, and S be the submodule of cuspidal families. Cuspidal families, I mean, it's the same definition like here, but the specializations here are cuspidal. So they are not only modular forms, but the constant term at all the cusps is 0. And we can define similarly the Hecke operators here. Sorry, before I didn't define what's the UP, but it has also, you can define it also on the Q expansion. And you can define them because it's an abstract Q expansion. You can define the TL and UP abstractly on the Q expansion such that they are compatible with the specialization. But what I want to say, this module has a geometric definition. It's somehow a section of a certain line bundle on an open of a modular curve. But I will not say more. You will see this after. And now the main theorem is the following. So first, Hida defined an ordinary projector using this Hecke operator. And he defined M ord as just the image of this module under the idempotent that he defined. And he showed the following. First, that this module and this one are finite and free lambda modules, both of them. This is quite nice because we know that the space of modular forms have finite dimensions. So if you see them over ZP, they should have finite rank over ZP. And Hida showed already this. Sorry, he showed the similar version, but just for the ordinary part. And he showed this control theorem, which is quite important because it's obvious from the definition that the specialization will land here. It's by definition, but he showed that the specialization is really subjective. So if you take any modular forms of weight k, which is ordinary, you can lift it in a lambda-adic family. And in particular, if you take eigenforms, because we are more interested in eigenforms, so not any modular form, but a modular form which is an eigenvector for all the Hecke operators, you can lift them to an eigenfamily here. And somehow he showed that the lift is unique when k is greater or equal to 2. And in weight 1, this doesn't work, but you will land in a bigger space. It's over-convergent. I will introduce it after. But in weight 2 or more, you will land in the space really of modular forms. And this is quite nice because if you can lift an eigenform to an eigenfamily, you can then deform the Galois representation attached to your modular form and also all the arithmetic invariants related to your modular form. But ordinary is a little bit restrictive, not too much, but you have few examples of modular forms, eigenforms, which are not ordinary. But if you pick in general an eigenform, what does mean by being ordinary? It means if you look to the coefficient AP in the Fourier expansion, this AP is not divisible by P, it's just this. So in general, I mean, if you take AP, it is an integer. I mean, for almost all the primes, it will not be divisible by p. And then you can do your deformation theory and lift it in a family. Now Coleman wanted to remove this condition of being ordinary. He wanted just to deform modular forms such that the AP is non-zero. We call them finite slope. Such that if the AP is non-zero, he wanted to study the deformations of modular forms. If the AP is equal zero, it's quite hard. I mean, there is no theory. And there is Coleman theory, but the difference for Coleman theory, you need to invert P. So you cannot work in a nice ring like this one. You need to take much more complicated ring. And then I need to introduce first where I can deform the weight first, because to modular form, you have already the weight. You need to be able to deform to understand the space where the weight lives. And then I will explain the main results. So first, I want to introduce here the modular curve. It's the modular curve is a proper smooth scheme of dimension 2, but of relative dimension 1 over Zp. And it represents the moduli space of generalized elliptic curves with certain structures. And it has a universal object on it. And what I want to say, if you take the complex, point of your of the modular curve here, you get just the quotient of this Poincaré half plane by gamma 1n, which is a Riemann surface. And you know, you have this theory of this correspondence between schemes over C, which are smooth and proper, and compact complex manifolds. It's called Gaga. And here, if you take the Gaga functor, you apply to this one, you get directly the quotient of the Poincaré half plane plus cusps, quotient by gamma 1n. And you can define an automorphic line bundle omega on X as the pullback of the relative differentials along the identity section. And then you can define modular forms of level k and weight k and level gamma 1n and coefficient in a ZP algebra A as the global sections. Here you take the sim power k of your sheaf. So at the end of the day, sorry, here I was a little bit sloppy. Here you can consider just Z and you invert n. You don't need to go to ZP, sorry, but you can take Z and invert n such that if you pick A equal to the complex numbers, you get the modular forms that I defined before. So at the end of the day, the modular forms, you can see them as a section on a certain line bundle on the modular curve. But with this definition, I mean, this uses really arithmetic schemes. You can take A, not only C, you can take it FP. You can take it, and so you can define modular forms with coefficient in FP or anything else. And now to do Pedic deformations, we need to use the theory of rigid analytic geometry, which is somehow analog to the theory of complex manifolds. So if you have a scheme, you can attach over Q, you can attach to it like smooth scheme. You can attach to it a complex manifold. Here you can do also the same. You can attach to it a p-adic, somehow p-adic manifold. They are called rigid analytic spaces. And the theory is somehow similar. You have the same topological space, but you have, you have the same set, but you have more opens. And the topology in the rigid analytic world is a bit more complicated. We use like Grothendieck topology. We cannot define union of two opens as we like. It's a bit more complicated, but it's quite similar. So now let X analytic be the rigid analytification of the generic fiber of X. I mean, X is a scheme over ZP. If you take the generic fiber, you get a curve over QP, and you take the rigid analytic space. So the set is the same, but you add more points. More opens. So often the opens, I mean, you will add them by taking an inequality, not an algebraic relation. And then not all the opens will be Zariski opens. This is the difference. And here you take EP minus 1 is a lift of the Hasse invariant. The Hasse invariant is a section in the special fiber such that it is equal to 1 at ordinary elliptic curves and 0 at supersangular points. So the support of the Hasse invariant in the special fiber is just the ordinary elliptic curves. And then you can always lift here because this sheaf is, this line bundle is very ample. I mean, omega itself has a positive degree, but with Riemann-Roch, you can check that it's very, you can check when it is very ample, and then you can show that you can, the H1 is 0 and you can lift it. So now we will define some admissible opens, xv as follow. I take x, all the x in the rigid analytic space satisfying this inequality, and this is really an admissible open. It's not a Zariski open. It's given by an inequality, not an algebraic equation. And in particular, if you take v equals 0, you get the ordinary locus, which is the complementary of the supersingular residue disks. Somehow you remove all the points corresponding to elliptic curves, which are supersingular mod P. And you can define the space of p-adic over convergent modular forms as the limit of the global sections of omega k on xv. Somehow you can think of them as sections on x, or that they, and you can extend them a little bit in the supersingular disk in some annuli. It's the picture. And you can define also an abstract Q expansion. So if you take the cusp infinity, for example, it corresponds to a section like this, and you take the completion along the infinity, you get that the completed, I mean, the formal scheme will be just zp double bracket q. And this will allow you to define a Q expansion, but you need to take suitable trivialization, because you have line bundle, then you restrict it to this formal scheme, and you get necessarily projective module over local ring, which is necessarily free. And you fix specific trivialization, because the universal elliptic curve around in a formal neighborhood of a cusp is just the Tate curve, and it has a specific, somehow canonical generator of the differential, which is dt over t. And under this trivialization, if you take any modular form, you can restrict it to, you can take the restriction to the stalk here, and under this identification, you get a Q expansion. And if you start with a modular form as I defined it before, you will get the same Q expansion, because the one that I defined before, it's really global section. It's not only on X, but it will be really global section. So you take the restriction here, and then you go to the stalk, and then you use trivialization. At the end, you get the same Q expansion. And the weight space is the space where I will define my, where I will deform my weights, because first I should be able to deform the weights before be able to deform modular forms. The weight space, you can think of it as the space representing homomorphisms from ZP to GM. And you can consider Z as a subset of the QP point of the weight space naturally. You take the character sending X to X power K. So if you pick K here, you take this character, it gives you a point in the weight space. And which is quite important, you need to know that the classical weights are dense, and they are dense here. They are even very Zariski dense. In regional geometry, we have the notion of Zariski dense, which is similar to the one in algebraic geometry, and very Zariski dense is a little bit more. And the weight space can be seen as the rigid analytic generic fiber of the Iwasawa algebra. This is like a copy of the Iwasawa algebra that we have seen before, p minus 2 copies. Or if you want to see it directly as a subspace of CP, of QP bar, it's union of disks of center 1 and reduce open disk and reduce 1. But for the Pedical topology, of course. So it's quite easy as a space. It is smooth and nice. And now, I mean, I will explain how we can deform modular forms. So the idea here, we see that modular forms are sections of this omega power k. So we need to deform this sheaf along the weight space. And it's what people did before. Coleman did it with another way, but it's better to, it is more modern to use the method of Andret Ayuvita Stevens. They constructed an admissible covering of the weight space. And the sequence here for the neighborhood of the ordinary locus, and an invertible line bundle on this product here. And the main property is the following. If you take any classical weight here, and you take the specialization of your line bundle along the classical weight, you will get a line bundle here, which is exactly omega power k. So you have a big sheaf interpolating omega k. I mean, I will not say a lot, but the idea, if you have a line bundle, you can attach to it a GM torsor. And what they did, they built an open for the rigid analytic geometry in this GM torsor to build a ZP star torsor. And then they could interpolate all the characters. And then they took like the K component of their torsor to get a line bundle. It's mainly what they did. But it's quite tricky to do it. They need really to understand the theory of p-divisible group of elliptic curves and stuff like this, and the Hochstate period. And it's quite tricky. Now we define the module of Coleman families as follow. Just the sections. And we can see if we take any specialization at any K, I get an over-convergent modular forms. So elements here interpolates over-convergent modular forms. And which is important here, the UP is a compact operator. And this space is a Frechet space. And without the limit, it's a Banach module. And UP is a compact operator. And so we have a slope decomposition. So the idea, you can cut this in two pieces, a piece where the UP acts by non-zero, and another piece where UP is nilpotent. And if we want to consider just the ordinary part, we will get the theory of, we'll get Hida's theory. So by slope decomposition theorem, you get the following. I mean, you apply if you apply the ordinary idempotent built by Hida to this space, you get a module which is locally free and of finite type. And you will see after that you can compare it to the module built by Hida. So if you take any Coleman family, you can attach to it Q expansion. As I explained before, sorry. You use always this trivialization here. And I want to highlight the cusp here belongs really to this locus. So it belongs to all the XV. I mean. And so here, if you take any Coleman family, you do the same. You do the local trivialization at the cusp, and you get Q expansion with coefficient in OBN. And by construction, I mean, and there is also a control theorem proved by Coleman. This abstract Q expansion will belong necessarily here. So because this will be the Q expansion of Coleman family here. And if you take specializations, if you take the ordinary part and you take specialization at weight K, 2 or more, you can show that you get over convergent modular form, but you can extend it to the whole modular curve, and then you get classical modular form, and this fits with the definition of this module. Because this one is like also abstract Q expansion, specializing to classical modular forms. But with Coleman, we can get more. We can here, because of the fineness of the composition, we can get, after shrinking this BM, or we take you cover it by smaller affinoids, you can decompose this as a part where you have finite slope. I mean, the UP acts by non-zero on the eigenforms, and the other part is, it will be nilpotent. And the finite slope part is also like locally free and of finite type. And so you can then consider like the eigencurve. So Coleman and Mazur constructed a rigid analytic curve over the weight space called the eigencurve, was the points correspond to all finite slope over convergent p-adic modular forms of level 1. So any point here, it has a weight here, and it will be a section. It will correspond to a section here. And omega k, because we said that we can define it even if k is not classical, say it's not in Z, using the interpolation done by Andrea Vita Piloni, and you get an element here, which is also an eigenform for all the Hecke operators. And Bazar generalized Coleman Mazur construction for any time level, because at the beginning they did it when n equal 1, and then he extended here to any n. And the rigid analytic curve here is flat and locally finite and proper over the weight space. And if you want to compare it with Hida theory, if you take the Hecke algebra, I mean the subring of the endomorphism of M ord generated by TL and UP, this one will be finite flat over lambda. And if you take the rigid generic fiber of it, it will be an admissible open here. So the theory of Coleman includes the theory of Hida. But the difference, I mean, the theory of Coleman, you have to invert P. The rings that we use are really like Tate algebra, not Iwasawa algebras like ZP double bracket X. And Hida family is, I mean, if you take an irreducible component of the spec H, it's the same take an irreducible component of the eigencurve. it will be, sorry, an irreducible component of C, but not any reducible component will be an component here. You have just one direction. It's called the Heda family, and it corresponds to an eigenfamily. And you can see it as follow. Here is the weight space. The classical weights, I mean, k equal 1, 2, 3, until infinity are all here, and they are dense. And above, you will have classical modular forms, but from weight 2 and more, you have classical modular forms, and they are dense here. And for the other ways, you have over convergent modular forms, not more. But this space, I mean, is smooth. This one, it's more complicated. We don't know. We have examples. No, I think we don't have an example where it is not smooth, but we have examples where two Heda families can cross. You will see one today. So now I want to introduce quickly I will give you an example of Heda family. So, I mean, the simplest example is Eisenstein series. The simple example is Eisenstein series. So you take an Dirichlet character, and there is a pedical function, is an analytic function over ZP satisfying the following condition. This omega p is the Teichmüller, the character that introduced at the beginning. If you evaluate it at 1 minus k, because 1 minus k lives also in ZP, because ZP contains Z, you get the classical L function and this Euler product with this Euler factor. So it's this L function, and you remove the Euler factor at P. And there is an element, I mean, I don't know who built it first, but you can find it in the Book of Washington, an element in the Iwasawa algebra satisfying this property. And it's often called like the Mellin transform of the pedical function. And why we need this element? Because a constant term of an Eisenstein series is given by this value. And so to be able to build an Eisenstein family, you need to interpolate all the coefficients. In general, all the coefficients are easy outside the constant term, but it's done by this by Kubota Leopold. And I want to highlight here, you have a 0 if the phi of p equal 1. Why? Because if you plug here 0, it means k equal 1, and then this Euler factor will vanish if and only if phi of p equal 1. This factor will never vanish at 0. And here it's called trivial 0 because we have a 0 for trivial reasons. The Euler factor, this factor will vanish. So you can then build Eisenstein series, Eisenstein families like this. The coefficients are given like this, and the constant term by this zeta function. Here, I mean, I use the Bernoulli notation, I mean. And the specialization, you can check it by hand at k equal 1 or 2 or more. You get what we call classical Eisenstein series. Because Eisenstein series, the coefficients are like linear combinations of the values of the characters at L. And it's quite easy to interpolate them. But the constant term is more involving because it's a certain L value. And now, I mean, we want to understand when an Eisenstein family like this meets a cuspidal Heda family. And I can tell you in advance, it will happen when we have a trivial 0, because naively, you see here, if you have a trivial 0, the specialization at 1 of this one will be 0 here. If phi of p equal 1, you will have, because of this relation, if you plug k1, you have a 0. And so, but it's just infinity. You need to be able to write what's the constant term at the other cusps. And using the abstract definition that I showed you, just using Heda theory, it's quite hard because it's just abstract Q expansion, how you can compute the constant term at cusps. So you need really to use the Coleman approach. So let D be the Weil divisor corresponding to the cusps of the modular curve. When I have the exact sequence of shifts here on this neighborhood of the ordinary locus product with Bm, here I'm a little bit sloppy. I need to take the push forward because you can see D product with Bm inside. But what I mean here, if you take the quotient of the two shifts, you get some skyscraper shift, and it corresponds just to the structural shift of this one, quotient by the shift of IDL of D. So a bit sloppy. And then you take the H0, you get a long exact sequence. And this one, it's like the elements here are cuspidal Coleman families, and elements here are Coleman families. And the quotient, because this is like the somehow skyscraper shift, is just the sum of the analytic functions on Bm on the cusp, because D is a finite number of points, cusps. And the H1 here will vanish because this space is an affinoid. It's similar to algebraic geometry. If you have a coherent sheaf over an affine scheme, the H1 or H2, all of them will vanish. And in complex geometry, this will be like somehow an analog of Stein space, and you have theorem of Cartan A and B. It's for similar, it's for analogous reason. And then when you take the limit on M here, you get what I defined before, like lambda-adic families, but I told you I need to invert always P. Because if I take the limit on M, I will recover all the weight space, and functions on the weight space are bounded function on the weight space are this lambda, and you invert P. And here I translated it in terms of Hida theory. And so I get really like somehow this map will send to an element here all the constant terms of the element. And we computed them by taking higher specialization. And we got that the constant terms are all multiple of this zeta. So now what you can say, if zeta has a 0 at certain k, then you are necessarily in the kernel when you take the specialization. So you have something cuspidal. It's the ID. So if phi of p equal 1, then you have here a 0. And then you just specialize your exact sequence in weight 1. And what you get here, it will have a constant term 0. So you will have something cuspidal. So it's what you get. You get it. This is weight 1 modular form, and it will be really cuspidal, minus d. I mean here minus d, I mean just you twist by the sheaf of ideal corresponding to the cusps, which is the dual of the line bundle attached to d. So if f is a p-adic cuspidal over convergent, so here you get that f is a p-adic cuspidal over convergent weight 1 eigenform, and it lives in the cuspidal locus of the eigenform, of the eigencurve. And also you can show there exists an ordinary lambda-adic cuspidal eigenform f in the language of Hida specializing to f, and with a coefficient infinite extension of lambda. And this is the picture. You have here an Eisenstein family. The Eisenstein family is isomorphic really to the weight space. It's like it's really a copy of the weight space. And here you have a Hida family, and they meet at the zeros thanks to this exact sequence. I mean, what I want to say, our main contribution for this exact sequence is like we did it using using coherent cohomology. And so we got new results. But before, people did it with algebraic topology tools, and they had to exclude this case. It was done by OTA, and they had to exclude this case. But when you do it with coherent cohomology, you can do it even for p equal 2, p equal 3, and any n. So the question now, we know that we have at least one family specializing to F, our weight 1 modular form, which is Eisenstein, but periodically cuspidal. So the question, how many cuspidal eigenfamilies will specialize to F? If the cuspidal eigencurve is smooth at F, and if the weight map is étale. And there is an order for such questions, because 3 will imply 2, because the weight space is smooth. If this is étale, it means like they are locally isomorphic. And if this is smooth, it means that the local ring has a unique irreducible component, and it means that you have a unique eigenfamily, because the reducible component correspond to eigenfamilies, I mean eigenvectors. And Darmon Lauder-Roger conjectured that 3 always holds. And this is now the main theorem of our work. We fix their question. So if we need this assumption such that F is periodically cuspidal, then we showed that this is étale. I mean, this is étale. And we computed even the local ring of the eigencurve at F. And you have 3 copies of lambda, which is the local ring of the weight space at the weight of F, meeting transversally. You can think of them like 3 lines meeting at the origin. And it is not Gorenstein. And you can write it here like this. And as applications, we could prove we could give new proof of the gross formula. We computed the derivative. I mean, we computed the derivative of the constant term of the Eisenstein series. It's how we did with new method. And we could show the non-vanishing of the congruence ideal. It's somehow an arithmetic invariant of the cuspidal family. And when phi is quadratic, this yields new cases in the local version of Hidati-Wien conjecture related to the Iwasawa main conjecture. It's the main applications. So I think I will stop here. And sorry, it took me more than what I thought. I really apologize. So I finish by some references if someone is interested.